Okay, this is for Maths 1C 15.5. We learn how to parametric surface. But before we do that, I'm going to call it with something so you know why we are doing this, okay? I want you to know the reason we are doing what we are doing right now. So let's record line integral first. We first learn about line integral, okay? What is a line integral? It means you integrate along the edge, okay, over the curve. So line integral basically is, we learn from 15.1 to 15.4, we're going to integrate over a curve. So this means, okay, that means integrate along a curve. Because we 1A, 1B, we learn how to integrate on the x-axis or on the y-axis. But now you learn how to integrate on this curve, okay? So C is a smooth curve first. It can be piecewise smooth, okay? What piecewise smooth means? It means that, like, for instance, we did a power line integral like this, right? C1, C2, C3, C4. So they don't smooth here, but they smooth on this piece, okay? C1, C2, C3, C4. So you're smooth on your own, okay? It means you're continuous on your domain. So that's called piecewise smooth. And then this curve is represented by a parametric equation. This is a parametric equation, okay? Xt, yt, and gt make up for rt. So when we do surface integral later on, we also need a parametric equation. So that's how we do on 15.5. We learn how to parameterize a surface. These integrals for parameterize this curve, okay? And then we have a scalar form for line integral, okay? So this little arc length, that is it, okay? Integrate on this one. Sometimes it's in the book, they like this. That's the same notation like that, okay? So now people don't write that anymore, they just write the C here. It means a line integral, okay? And counterclockwise. So that's why it's in the arrow like that. You wonder, hey, why are they? But we don't use that notation anymore because it takes a long time to write that. So people just like this, okay? So this represents arc length. And then the application for line integral is the work done along the curve. What do you mean by work done? Could be circulation for heat, or for water, or for liquid, or for electricity, okay? So let's say if this is an electricity field, it's going like this, let's say, and that's your F, okay? The vector field, electricity field. And then if you want to find out how much electricity going through this curve, that is a line integral, okay? That's what line integral used for application. So application line integral, anything flows, any circulation go around the edge, okay? The work done, okay, work done along the curve, the formula is work done equal to C, okay, C means the curve, F, that's a vector field, okay, the vector field here, okay, and then that's dr, that's by the derivative of the parametric equation represent, or parametric function represent the edge, okay, represent the curve. So that's same as a derivative. You can do one more step, that will be r prime t dt, okay? So that's a parameter, t is a parameter. There are two important theorems for line integral. Two very important theorems for line integral. One is a fundamental theorem line integral. That's for conservative vector field. Use this one, it's easier. And second is a green theorem. Green theorem, it can use for conservative also, but no need to do that because they're just going with zero. You may just use this one. But you can use the green theorem also. But green theorem is mainly focused on not conservative. It's more useful for that, okay? So that's how, so fundamental theorem line integrals for conservative, and this is not conservative. I mean, now remember, okay, this is not like 100% you cannot use a conservative for green theorem. You can, but there's no need to, okay? If you are conservative, you may as well just stay with this one. And that's when you calculate work done for the application of a line integral. And what's conservative means? Conservative means that no twisting, no pushing force, okay? So every place in the vector field, it behaves the same, okay? It's not like, oh, you come here, all of a sudden the force becomes stronger. So it's not going to be like that. Not conservative, that means that is happening now, okay? The electricity, maybe all of a sudden when they flow to a particular point, maybe like too much or nothing. So kind of like extreme, okay? So they don't behave the same on every point in the vector field. In that case, it will be not conservative. So that's what we learned in line integral, okay? You can see that line integral, they require parametric equation. We know how to do the parametric equation before, like for circle, right? I gave you guys for circle, for line, for ellipse, okay? Hyperbola or parabola or any other type of, you just need to follow the rule we learned before, okay? So the rule we learned before, the parametric equation we learned before, okay, is, I'm going to just give you a couple examples, okay? But you guys probably know it, you already knew it, but I'm going to just remind you. So for instance, for line, okay, we say, hey, we can parameterize a line like this. Okay, so it's R0, and then 1 minus t plus R1, and then t. And that was what we did before, right? So that's for line. And then we learned about circle also. So for circle, and then we have x equal to R cosine t, y is equal to R sine t. There's a center at 0, 0, okay? If not 0, 0, then you need to add a center here. Let's say h plus, and this is center at here, k plus. And so on, these all parameterize when we do just a curve, okay? This is a simple curve. It's not a surface. It's not a surface. But when you parameterize a surface, then you have totally different story, okay? It's much harder. So now, 15.5, I teach you how to parameterize the surface. Because we're going to learn surface integral from 15.6 on. Okay, 15.5, we're going to learn about how to parameterize first. So, before we go to 15.6, the most important lesson start from surface integral. Let me introduce you what surface integral before we learn how to parameterize first, okay? So you need to know why you want to learn surface integral. So what's a surface integral? It basically, let's say so this is for surface integral. So on 15.5, we learn how to parameterize a surface, okay? To parameterize a surface. To parametrize a surface, okay? Why want to do that? Then why? That's because we're going to go into a surface integral. There's a second, I told you guys that we're going to learn 4 very important theorems in vector calculus, okay? So surface integral contains 2 of them. It's a divergence theorem and Stokes theorems. Oh, by the way, still who's going to go to UCSD? Now UCSD has 2 classes. One is called vector calculus, one is called multivariable calculus. Our class include both of them. So if they want to take a vector calculus, make sure you take a challenger test, okay? Because our many students, I tell them they just go to challenger test out, because challenger test, they basically is what you learn here, okay? You take the exam, then they will let you bypass that class. But you have to do that before you start registering for that class, okay? Make sure you take care of that before once you go there, you let them know that I need to take a challenger test for vector calculus. You basically review math 1C, you should be okay. So what's this? So to parameterize surface, why do you want to do that? Because we need to learn surface integral, and we need to know what's the parametric equation to present the surface integral? So why do I have to learn surface integral? Because we have to use this surface integral to do a very two important theorem. I told you, divergence theorem and Stokes theorem. And so what is the surface integral then? What is it? Surface integral means you integrate over a surface. Okay, so for instance, if I have a surface right here, and that's a surface, okay, it's a curve. So I use the S to represent my surface. And then if I want to see electricity flow across the surface, okay, let's say I've electricity across the surface, okay, or heat or liquid, okay. So for instance, if you're holding a bottle of water, okay, and you open the cap, and then the water going to come out and splash on the surface, and surface integral to see what's the speed what's the speed for the water to run across the surface, okay. That's what the surface integral for. Or what's the heat, okay. If you're going to put current, electricity going through this surface, we want to know what's the speed for this electricity cross that, okay. So physics engineer use a lot of surface integral. They also use a line integral. Line integral to just check the edge. Surface integral check the surface. So this is surface, okay. We have to parameterize it, okay, because we have to see what kind of function can represent the surface. So that's what we do, okay. Just like how we do the line integral, we have RT equal ST, YT, and GT, right? And then we have a specific line for other geometric figure. So for surface integral, we do the same thing. You know, we want to see what kind of surface, okay. Now when we learn in 11.66, we learn like a two surface, right? Quadratic surface and cylinder, okay. So how do we represent function for those kind of surface? So that's basically, and represented by parameter t. So that's what we do for surface integral. So surface integral basically integrate over a surface. And then I was right now in this session we just learn how to parameterize it, the surface. We are not going to go into detail on surface integral. Surface integral also have just like line integral, they also have a scalar and application. The application is a flux, okay. That means how fast things change. I mean, what's the speed they change. I will, when we go to 15.6, I will go detail on that. Now we just give you a little bit starting point so you understand why we are doing that, okay. Why do we have a parameterized surface? Because we calculate first. So now I'm going to teach you how to parameterize a surface first. And so here is a let's say I have here's a definition, okay. And if you have a plane, okay, these are planes. Now remember in line integral we use a t as a parameter, okay. In surface we have two, right? We have two, not just a t itself. So therefore they use a u and v, okay. Now it can be something else later on too, because it associates two parameters. So they use u and v, and then they said they have a region here, okay, and they call this the original region. It's a flat. Now this is a flat here. They use a d, and then this is a two dimension here, okay. And then there's a point here. This is a point is uv, a point uv. Now when you go to three dimension, and this is a curve. This is on the two dimension looking, okay. In the three dimension, it can be looks like this. okay? And then that base looks like a, okay, then on the other side you don't see it, okay? So this is the 3D looking, okay? So this is S now, this is surface. And this point here, okay, this point goes to here, so maybe it goes to, on this by here, let's say it's close to it, okay? So maybe a little bit, or maybe, so on the 3-dimension part right here, okay? And then once you get to here, that point on the 2-dimension, go to 3-dimension, you become a vector. Okay, this is, oh. Okay, so this point here, it become a vector. This vector I'm going to use. Okay, so a point in UV plane. A point in UV plane, okay, becomes a vector in, let's say this is X, Y, Z. In S, Y, Z coordinate. Okay, so, and now there's a two-way to parameterize this, okay? So let's say if, so the two-way, okay? If the surface function, okay? So the surface function, next time I'm going to use it, Z is equal to G X Y, okay? So that's a surface function. This is a surface function. Sorry, I had to write very small, not enough room. So this is a surface function represent. This is surface, okay? Let's say it's a G equal to G X Y. I tell you why I don't use the F. I'll tell you later on, okay? In the next session. And then, so I use a G for the surface function. And if G equal to G X Y is not given to you, okay, that will be a problem. If it's not given to you, then you need to parameterize it. This is surface. Then the surface by using this RUV, okay, RUV, okay, then you need to use this point, this vector here, okay, because your point become a vector now, okay, so this vector will represent the function for this surface, okay, will equal to X UV, Y UV, and then Z UV. Okay, this is the function UV, okay, and someone said, can you use other thing? You can, okay, we just use UV here. These are parametric surface, okay. These are called parametric surface, okay. These are called, so parametric surface, so by this vector function, so this is called a parametric okay, and all these are called parametric equations, okay. So this is 3, and we don't want that because that will make things a lot harder. This is called the parametric equation. So when this is not given to you, then you start running into trouble, because then you have to parameterize this. But sometimes some surface is very easy to parametric. So they parametric by using this vector here, okay? And then they find out what's the point represent this vector, okay? And this vector is represented by this three parametric equation right here, right, this point. And then this is called, then you parameterize this surface. So that's when this is not given to you, okay? So this is not given to you. Now, would they always not given to you? No, I would say half. Sometimes we get problem that I run into maybe half the problem given is not given, this one, not given, then you parametric. But then the other half is given to you, okay? So now when it's given to you, if this is given to you, then things become not easier. Then we can use a gradient to do the problems. Because remember we learned gradient in chapter 13, and then in chapter 13:7, we learned how to find the tangent plane on the surface by using the gradient as a normal vector. Well, that is because the surface function is given to you. Then you can use a gradient. But if it's not given to you, then you couldn't, right? So we're going to do a problem then later on. Then it's not given to you. How do you find a surface function, surface equation? Okay. So the second, this is the first situation. The second situation is if this is great. We love this one. If this is given to you, okay, then it become easier now. You first need to find if this is given to you, okay, then, well, we haven't do the gradient yet, so I couldn't tell you yet, okay. So I will just give you this first. Then your RT, now you don't need to use the, or I use RSY first. You don't need to use UV plane, okay. If this one is given to you, and then you just need to find the RSY, okay. You don't have to convert to UV, okay. You just use the RSY. So the picture I have earlier, okay. Okay, let's say this is a point right here, okay, and this is X, Y, Z, X, Y, it's Z, okay, and then I just need to find this vector, and then there are R, X, Y, okay. I don't need to convert the UV plane like earlier. That's because this is given to me. It's a given. Okay, if this is if the function is given to you, okay, if the surface function is given to you, like this is a surface function, if a surface function is given to you, you do not need the UV plane to transform. Okay, you just go ahead to get the point, draw your vector, find the parametric for this vector, then you're done. Okay, the parametric for this vector will be X, Y, and Z, and then XY. Everything convert to XY only, because this means that you can only have an XY in your function, okay? So that is a GXY. I use either G or GXY, sorry. And then, so that's for if you're going to, this is given to you, okay? If this is given to you, things become very, very easy, okay? And we will do that in chapter 15.6. We will see in that, okay? So how easy it is. Next thing is, we learn how to find a normal vector when this is not given to you in the first situation, okay? So I'm going to erase this part. And I'm going to erase this one. This is not given to me, okay? Not given. Okay, and then now the next thing is I need to find a normal vector. Let's say this is not given, so I'm going to erase this one. Okay, maybe I write right here. If G, the surface function, is not given, okay, how do we find a normal vector? A normal vector vector. So let's say I use an n. They're perpendicular to the surface. Perpendicular to the surface at a point. Okay, so I'm going to continue to use the same surface here. Okay, and as let's have a point here. Okay, so this is surface, so you can see the 3D looking, hopefully. Okay, so this is surface. Okay, and then there's a point right here. I said, can you, let's say I'm going to give a point a name, so x0, y0, and z0. Okay, I said, can you find a vector perpendicular to this one? Oh, sorry. So I had to erase this one right here. Okay. And then I said, can you find a vector, normal vector here? Okay. That is perpendicular to this surface. Perpendicular to it. Then you say, I'll just find the gradient. That's what we did, right? In 13.6. In 13.7, we used that to find that we can able to find we are able to find, I want to get something. We are able to find a tangent plane that crosses the surface, okay? Across this point, tangent to the surface. That's because I am given the function that represent the surface. Then you can just find the gradient. But this time I don't even know what function represent this one. Don't know. Then what you need to do, you must have to use the UV plane now. The UV plane we have earlier. So we're going to find a derivative, okay, partial derivative for RV. So change this to UV plane. Like this is 3 dimension here, okay. And then I'm gonna convert this to be a V, and this is a U, okay. And then I change to a UV plane, and then this point, okay, I'm gonna find a vector partial derivative parallel to the V, so that will be RV, okay, partial derivative parallel to V, and then I will partial derivative parallel to U. So I put RU. And then your n is just the cross product of these two. Okay, your n is equal to, I don't have a long on this side. So it's RV cross RU. Oh no, RU cross RV, sorry. Okay, so that's your normal vector. Okay, and here's what you need to first, and I'm going to state this: S is a smooth surface. Okay, and your R UV, we're going to use the one I gave you guys. When this is not given to you, I gave the equation, the function, the parametric function represent the UV. So it's X UV, Y UV, and then Z UV. Remember the one I gave you earlier? I just give to you again. Okay, D. Okay, D. The earlier I give you the D. So I convert back to a 2 dimension here. Okay, but in 3 dimension, that's what it look like. D is the open region. Open region in UV plane. And then your normal vector, okay, you convert the S0, Y0, Z0 to be a UV, to be, I use a U0, V0. Okay, you convert that. So S0, y0, z0, a point in the xyz, you go back to u0, v0. Okay, and your normal vector n is a vector perpendicular to s. Okay, and your I'm just list all the thing we use, and your n is equal to the cross product RU cross RV, and this is not equal to 0. Okay, if equal to 0, there's nothing you can do about it now, right? There's nothing for you to do. And then there's a tangent plane will cross this one. Okay, so I'm going to erase this part, and maybe I draw a tangent plane. So let's see how I'm going to draw this. Okay, I do my best. Okay, so this is a tangent plane here. We'll cross this u0, v0. So the orange one is a tangent plane. Okay. Okay, so when we need to find the tangent plane here, okay, we need to find the normal vector. So normal vector is the cross product that. Now I'm going to show you, so I'm going to erase this one. Okay, and your normal vector and is equal to RU cross RV, okay, is equal to IJK del X to del U, del Y to del U, del Z to del U. There's a partial derivative on U from the XYZ function, okay? XYZ parametric equation. And then this is a del X to del V, del Y to del V, and then del Z to del V. So remember the function I gave you guys earlier, right? RUV, this is a function, that's where it comes from, okay? RUV equal to that one, X, Y, Z. And they'll have UV here. Remember, I don't have enough room to write it, so you need to, so this is for UV, okay? So that's where they get this X for this one, Y for this one, Z for this one. That's where they get that. And then, now once you get this, then we know how to find the equation of the plane, okay? Then we're going to do example later on. But before we do that, let me give you a couple important parameterize things first, okay? How to parameterize a surface now. Means how do you find this XYZ? Because the line we know for line integral, we know. Now I gave you guys already, but what about for surface? Okay, so here's a problem number 18. They said the plane. Yeah, I don't think I gave you homework for these sessions, because we are talking about time permit, but because we have time, so I'm going to, the homework will be, let me give you the homework assignment to practice, okay, before I forget, 15.5, okay, you just need to do, not that many, okay, 17 to the homework on 15.5 will be 17 to 25 up. This is pretty easy, just a parameterized surface. And then 33, that's it, okay? The rest of we are not going to do it because the rest of remaining none this is for 15.6. So 15.6 we're going to do more. So the plane is x plus y plus z equal to 6. And then, okay, so they want to parameterize this plane. Well, that's very nice. The function, the surface functions are given to you. Okay, so you can solve for z out first. That's given to you. Then you don't need to use a UV plane. Okay, like it's given to you. Your R, just use xy equal to x, y, z, and then convert the z to here, so be x, y, 6 minus x minus y. Okay, so what is x, y? If the x, y here, then everything will be x, y only. Okay, for something else, then follows that. Okay, so you cannot for x, y, and then a z here. So z need to convert it in terms of x and y. So that's all you need to do. So it's pretty straightforward. And then number 20. So that's why we want the parameter, we want the surface function given. If it's given to you, it's really easy. These are the cone. The cone is x equal to 16y squared plus z squared. Again, the function given to you, although it's x in terms of y and z, but they still is a function. Now remember, it's not like you have to be z all the time. It can be x or y as the dependent variable. Okay, it can be. Okay, so it depends on the point given to you. If they give you like this, then how do you parameter then? Then you're going to keep your yz as the one you use. And then your x become this one. And then you just have y and z. Okay, so that's how you parameterize this cone. Okay, now here's the important one, to parameterize the cylinder. Okay, because cylinder we use very often. Okay, how do you parameterize the cylinder? Okay, parametric cylinders. Okay, oh, I don't need the S here. So the parametric cylinder, basically you're going to use, okay, because cylinder usually given to, I'm going to just use one of them. Okay, so now x squared plus y squared equal to r squared is a cylinder, right? We know that. Okay, so then z is missing. So who's missing? Okay, and we use this one so often because this is like this. Okay, and let's say this is my x, y, z, okay, and that's my r here. So this is cylinder, this is shape we use often, but sometimes it can be other shape. Okay, it can be like this. Okay, the cylinder can be slipping like that. Okay, so we just use one of them, the other one be same. Okay, let me tell you. So you can see the z is missing, right? The z is missing. So when the z is missing, so z can be go as high as you want to, unless you restrict by z. Then yeah, you can restrict it, but again, z is missing. When the one is missing, you put it right here. Okay, and then how big your circle is, it depends on your theta. That right? Okay, and your r's already restricted. How they circulate this one? Okay, because you need the theta. Okay, you need the theta to turn to make the circle, right? To make the circle here. Okay, you need the theta turning. Okay, so therefore you need theta. Okay, so you need the z, you are missing the z. Okay, you need the theta because theta turns to create a circle. Okay, not how big the circle, that was my mistake. I mean to create a circle. Okay, you need the theta. So that's why your parameter will be z and theta. That's how it comes from. If I want to use this one, okay, if I need to do a problem for this one, for this cylinder sleeping on the floor, and then now this time your R, now you're not using, you're missing it all. This time you'll be x squared plus g squared equal to r squared now. Is that right? Okay. Like last time I seen a problem that one of my students sent it to me, UCLA. That's the exam actually. So this time you do not use. So he said, "Oh, thank you for pointing that out, because when I teach 1C last year, I mentioned that if you are this time this is the scene that represent this graph, okay? So that you can see the y is missing, that right? Y is missing. Then you need to go, okay? Then you need to go like that. You can follow me here. Then your circle be your circle is actually projected on the xz plane, okay? Xz plane. So this is circles are projected on the xy plane. So xy plane will look like this, okay? So this is xy plane, but this one is projected on this plane, okay? But this plane is your xz plane, and your y is missing. Y is missing. So then when you parameterize, you don't use a z here, you aren't going to get the right answer, okay? So this is the one that you're missing. That's when you're going to put right here. But 99% of the time you can see it's a z. But sometimes you can see like this. Or could be the other way. Could be the cylinder like this way. Okay? And then you can see then your x is missing. Okay? Then your x can go as long as you want to. Then you put x here. You guys follow me here? So make sure you do not always say, oh, this has to be z all the time. No. It depends on how your cylinder was placed, okay? Although 99% of the time you see like that. So I just picked this one because this one appear all the time, but I pointed out it can be any of these two, okay? So r theta g, then you use x, y, z, right? But remember, you can only contain a g and theta inside here, okay? You cannot contain x, y. You can have a z, but you cannot have an x and y, okay? You have to follow this one because you want these two as a parameter. So your x become, well, let's remember, r cosine theta, is that right? That's what we did for line integral, okay? That is what we use, or r cosine t. But because we use theta now, so you theta here, okay? So, and then your y is equal to what? Polar coordinate, or same as a polar coordinate, okay? And then all parameter equations, okay? So all the same here. So then you have r sine t, or I sine theta, and then you keep the z here, okay? So that's how you do, okay? And your theta cannot be more than 2 pi, of course. And so that is for that, okay? Parametric cylinder. And what happens for cylinder, okay? It's not made up by a circle at the bottom. So this one's the S5 plane is a circle, okay? Like this, both are. So this one's for, I'm going to put right here, x squared plus y squared equal r squared. So that's what it's for. What happens? You're not, okay? So if you have x squared over a squared plus y squared over b squared is equal to 1. If it's like a ellipse, okay, you can have a cylinder that looks like an ellipse, like they kind of like in the bottom, they're like this flat, so instead of a circle, they are like an ellipse in the bottom here, okay, it's not rounded. In that case, how do you parameterize them, okay? And we still use, so I'm going to still use this one, okay? And then now this time you are not going to have the same r here. Instead, what do you have? You're going to have a is underneath the x, so it's a cosine theta, okay? And then b sine theta, and then z. So you're going to have this. And maybe at least one more thing, that z is between z is h, okay? So It doesn't matter though. If they give you a Z, then that's good. They don't give you Z, that means it go as high as they want to. So that's for parameterize a cylinder surface, okay? So cylinder surface, either the circle on the top and bottom, or could be ellipse on the top and bottom. So that's the first one. Second one, we learn how to parameterize a sphere or ellipsoid. It's also two situations. Either they looks like a ball or they looks like a ellipsoid. Parameterize a sphere first. Okay, so parameterize sphere, and then we're going to use R. So what they do is that they use a phi and theta this time. Why they want to use a phi and theta? Because of, so let's say I have a sphere, okay, and the theta is right here, okay, and theta tells you you're going to complete a whole circle or not, okay, so theta is you complete a whole circle, okay, and then your phi is the one that means you're going vertical, so you go, the theta is go to flat x and y, and the phi is going vertical, okay, so be like this. Okay, so this one can only go to all the way to here. Okay, you go all the way, then you complete this half. But because this one, the theta helps you to you go all around, so that means you complete half here, the another half will come out automatically because it's only covered by theta. So that's why they use the parameter they use is a phi and theta. Okay, it's also equal to x, y, z. Well, that's also a problem because you're not allowed to use anything not from here, right? So you need to convert. So we use a spherical coordinate, okay? And then it becomes x equal to rho, okay, sine phi, and then cosine theta. Y is equal to rho, sine phi, sine theta. And z equal to rho, cosine phi. So I think that is a... Make sure I didn't make a mistake. So that's, you just go back to the spherical coordinate, okay, to get the x, y, z. And now if this is a ellipsoid, like this is for sphere, okay, for ellipsoid, okay, you also use the same thing. Because this is the sphere formula, maybe I should write it for you, just remind you, it's like this. Okay, now for ellipsoid, okay, that's for ellipsoid. Or they can use so that's for ellipsoid, that's for sphere, okay? And I use ABC here. So then you comes out to be A, B, oh, I don't have it. And then C. So that's how you do for ellipsoid. So now these are the two we use very often in 1C, okay? These are two. Sometimes we use a cone also, but these two use very often. Now we learn how to do a couple problems. Let's look at number 22. Don't forget the homework here. So I erase it now, and you can just rewind it to look at the homework. And that's one good thing about the video. Then you can rewind and pause and like that. Okay, they said parametric, a cylinder This cylinder is made up by 4 cylinder surface, okay? 4x squared plus y squared equals 16. Well, divide this and make it to be 1 first. That's easy for you to see what you need to use parameter. X squared over 4 plus y squared equal to 1. And then this is a cylinder surface, right? Because G is missing, so that therefore will be, okay, G theta. Theta means G means you're missing G. Theta means you're going to complete the whole xy plane, okay? So that's equal to, that's your A is equal to, okay, A squared is 4, right? A equal to, B is equal to 1. So that would be 2 cosine theta, y is equal to 1 sine theta. So I don't need to write the 1. And then your G, I can have the G because G is right here. So anything is right here, you can have that. You don't have it, you don't have. Okay, this have to follow this. And oh no, why did I become 1 now? Good thing. 16 is a 4, sorry. When I divide it, this is 1, this I'm thinking 1 again. See, that's why I need you guys to be in the class. When I'm in class, I know some students will tell me, oh, Miss Johnson, make a mistake. And when I teach myself, it's kind of weird because I don't have anyone respond for me. Like, do you guys understand it? No one respond. So if I make a mistake here and then no one can point it out to me. You probably point it out right now, but I couldn't hear. So anyway, I missed the class and then, but that's how things is. So we just make the best of it. Number 24, ellipsoid. Ellipsoid. And this ellipsoid is made up by x squared over 9 plus y squared over 4 plus g squared over 1 equal 1. And so you can see A is equals 3, B is equal 2, C equal to 1. And then when you parameter a ellipsoid, okay, we're going to use the R and then phi and theta because you need these 2 to make a ellipsoid, okay? And you can see because you need to go around here and then go around the top, so then you make a ellipsoid. And that's equal to 3 sine phi cosine theta. It's very easy for me to remember this. You know why? Because this just like polar coordinate, right? Polar coordinate is a cosine, and you just add a sine phi there. And then for y, you go 2 sine phi, that's not changing, and then sine theta. For g, you just become, because you only use the sine phi, then it has to be cosine phi. So it's not that hard to memorize, okay? And so that's how you do for number 24. Then we're going to do a number 26. We use a 22 and 24 the most, actually. But I'm going to just do 26 just to, just a little bit more. 26, they said that they want to find the part of the parabola. Okay, number 26. It's not that much harder, this problem. It's just the way they answer you. They said, here's a paraboloid, LOID. We have that in the exam last time, x squared plus y squared. Okay, it's like a bowl, okay? Lies inside the cylinder. The cylinder lies inside cylinder, x squared plus y squared equal to 9. First of all, let's see, okay? So I have to, let's see, okay? So I'm going to I leave a little room here first, okay? Here's a solution. I need to have R, G, theta, that right? I need to have that. So I need to find out what my z is, okay? Well, it's x, y, z, right? I have to be like it, but z has to change in terms of x and y, so we use this one. So z is equal to x squared plus y squared. The intercept, okay, lies inside the cylinder, so that means that this ball is inside the cylinder. So the cylinder is like this. There's a cylinder here, and then there's a ball. This ball is like this. And then chords keep going out, and they want to adjust this part. They present the surface this part, okay? So S, Y, Z, so that means the intercept, this is the intercept right here. So the intercept is the x squared plus, so S equals R squared, is that right? So this is equal to R squared, right? So that means that Z is equal to R squared. And then your R is between what? Your R is equal to square root Z. And your R is between 0 to 3. Because R squared equal what? 9, is that right? So this is equal to 9. Okay? So R just equal to what? Square root Z, so equal to what? 3. So between 0 to 3. And then, so now we're going to put it inside. Oh, there one more thing you said, why is it 0? That's because since there's a y, when no one asks me question, I kind of feel funny. Sometimes I could miss it because this ball here has to be above the xy plane. So that's why they couldn't go underneath, okay? So that's why R is between 0 to 3 because the R is equal to square root Z, so the R has a positive. Okay, so it's only between 0 to 3 for the R. So when you find the intercept point, so the intercept here, okay, this the whole thing is the intercept. Remember I sent you guys how to find R. The whole thing is R here, okay. So this R is between 0 all the way to the top. The most you can go to the top, and then to 3. The top the cylinder. Okay, you can go as a Y, but that's not my intercept anymore. So the intercept is only this part, okay, only inside here. So that's why it's R between 0 to 3. Okay, so that's how you find it. And if you have any other question, feel free to ask me. Sometimes I forget. You can send me a message, and then I can answer you also. And then X here, okay, your X equal to R cosine theta because it's circle, okay. And then y is equal to r sine theta. And your z is equal to r squared. So make sure you can have r squared, okay, because r is a constant, okay. You just only can for z and theta, but your r is okay, okay, r is okay, because r is a number here. R is between 0 to 3. So now the last thing we're gonna do is how to find, oh no, I have more than that. And now we're going to learn how to do problems. This is a long video, I'm sorry, but I go a little bit slower to explain a little bit more. So now we're gonna learn how to find number 35. Find the tangent line, find the tangent, not tangent, tangent plane. Find the tangent plane equations. For the surface. Okay, this is surface made up by it's very nice they parameterize the surface for you already, but most of the time they don't, okay? It's just a this session they do. Or 3u, 3u. And then u squared. Okay, so this is surface. That means the surface function is not given. That's why this is a parametric function. Okay, and so they want to find the equation for that, for the touch this surface. Okay, so we need to find the normal vector first. Okay, so let's find RU first. RU means the positive derivative with respect to U. So to take the RU, it's just equal to 2 cosine V. Okay, because that's 1. And 3 sine V. And then 2U. And then RV equal to negative 2U sine V. And then 3U cosine V. And then 0. Okay, and then take the cross product. I, J, K. Or you don't have, we have to do one more thing before we can take that. You can do like this, but then you have more work. So what I do is that I'm going to find the point first. Because I forget to put down one of the, they want to find the tangent for a surface. I thought this is a point, I forgot the second part. Through point 0.64. I mean, so I can do this, but if I find the point first, it's a little bit easier, okay? Little bit easier. Because I want to plug the points in first, then it's a little bit easier to do. So now this is a 0.64. Is a x0, y0, z0. I need to convert to a point uv. Okay, and how do you convert it? Okay, so you have a x equal to, so this is x, y, z. So x equal to 2u cosine v. Okay, and then your x equal to 0. That tells you, well, for easier to look for this one first. Y is equal to 3u sine v, and then y is equal to 6. Okay, or you can put a 0 here. And then u, z is equal to u squared, z is equal to 4. Do this one first, easier. So that means u is equal to 2. Okay. So u is equal to 2, so you have a 6 equal to 3 times 2, also 6 sine v. So sine v is equal to 1, so v is equal to power 2. And then if I take this one, I will also get power 2 because the cosine equal to 0, so power 2. So therefore your uv, you put it back here, that'd be 2 and then power 2. And then now you put it inside, okay? So I'm going to erase this part. So I'm going to erase now, okay? 2, I just need to remember 2 power 2. Then I'm going to put it inside here, okay? So your R U will equal to 2 power 2, so that's a 0, okay? Cosine power 2 equals 0. This is also 3 and then 4. Okay, so that's for the first. I put in the 2 power 2 inside. Inside here, okay. And then your RV equal to U is equal to sine, that's negative 4. And then V is equal to power 2 is 0. So that's why it's a lot easier to do like that way. Now you take the cross product. Because at home, I mean, when I first do the problem, I also forget about it. So I did, that's a lot harder to do. So do this is a lot faster. Okay, go I, J, K, 0, 3, 4, negative 4, 0, 0. There's many different ways to do a problem, but there's some ways a little bit faster. So it comes out equal to 0, negative 16, and 12. Because this is a equation, it will equal to 0 on the other side, so you can take it out, okay? You can use it 0, negative 4, and 3, okay? And then now we're going to put into the equation for the tangent plane. So I'm going to erase that. So that'll be, this is my vector here, so 0, x minus 0, plus minus 4, y minus 6, and then plus 3, z minus 4 equals 0. And you simplify it, it comes like 4y minus 3z equals 12. So that's how you find the tangent plane equations if the surface function is not given to you. If not given to you, you parameterize the surface function, and they gave that to you. That's very nice, but if they are not given to you, you need to parameter yourself, okay? And the last thing I'm going to do in this session, I'm just going to go very quick. The last part is the surface area. How do you find a surface area from a parametric equations, okay? So we are not going to find a surface area in this session, but we will do it in the next session. So if, okay, z equal to gxy. Now this can be x, it can be x equal to g yz like that, okay? But just that we happen to use this very often, so I just use this one. Depending on how your surface look. So if g equal to gy is a given, it's not given, then parameterize the surface first, okay? Parameter the surface by using the UV plane. Okay. Do this one first, okay? And then your surface, so the surface area, we use the SA, okay? SA will equal to okay, both are represented surface, okay? Now because the area, so you don't have any function between them, so these are surface, both these both are represent surface. And that's just a little, so this is a, you can think of that like little surface. It's kind of like this, okay? So that's this is a surface here, and right here, little bit. Okay, that's your dx. They write big because they don't want to use because when we write small, that's arc length, like what we do in line integral. So they write big. So that means a little. Now this is a capital letter. Okay. It represents a little surface area. Okay, it represents little surface area, and then it just equal to. It becomes a region D, or you can use R. So either way, you can either use R or use a D. Earlier I used a D for that one. I just follow the book, but normally we just use R. You can use a D also. Okay, that's the same one. And you change the UV plane. I think I already write the formula for you guys last time on the surface area. So I'm not going to write again. So take the cross product. And so that's if it's not given to you. Okay, I think I did write this formula for you guys last time. I don't remember I did or not. it basically what they do is that they convert this to UV plane, because I didn't know if I should make the video that long, so maybe I go quickly to tell you. Okay, so where this come from is come from like this. Okay, so there's a region R here, or use a D. Earlier I used a D, but you can use a D or R. Okay, so if I want to find the area for this one, I chop it, right? And then this is for the flat. Okay, this is a UV, so 2 dimension. And then I take one of them out. Okay, one of these little out here. So let's say this one's is this. So this is delta U and delta V. Okay, so the area for this rectangle, so the area for this little rectangle is equal to delta U times by time. This is a time, okay? This is a times. This is a time here times delta V, okay? Now these are times, okay? Not that product, because it's not a vector, just a length. But when you transform to here, so transform to this part right here, okay? So I take out this part right here, so you have to use a tangent plane. Remember that when we do the tangent plane, I don't know if you guys remember, so this is from chapter 13. So when we have tangent plane here, okay? So for the tangent plane, find the surface area, okay? For this tangent plane here, so this part right here, this little part right here, that you have to use a vector. Okay, the vector will be RU times by the length of these vectors, RU times by delta U. Okay, and then this part, the length of this part will be RV, okay, the length of vector RV times by delta V. Okay, and then now when you find the area of this parallelogram, you take the cross product, okay, the length of cross product. Okay, and then that's when we factor out the delta V, delta U, and then it becomes dA. Okay, so that's when we get this a cross product here. It's a cross product. Okay, I think I did this one before, so I use the U first. Or you can use, that's a U first, I'm sorry. I keep using V first, I don't know why. So the U, and then U. V, and then V. Okay, and then that's just for a little bit of it. When you do a bunch of them, okay, that's when you become like here, and then a dA. So dA just a delta U times by delta V. Okay, and then we factor out the delta U, and then factor out the delta V, and then eventually it becomes like this formula. And then so this is if G is not given to you. What happens if G is given to you? Like this is a formula for surface area. Okay, if G is given, if G equal to is given, then you just use the formula from before, okay? The surface function, okay? Like G, this is surface function. this is given, then your surface area, we'll use the way we did before. Then I also divide more on that formula in that R. So if you want to read that from the previous one, okay, then it's a lot easier. Now, this time I'm going to show you these two are actually equal to each other. Maybe I just show it to you now, but the video gets a little bit long. So maybe I just show it to you now, okay? So, RT, how to show that the surface, that this is for, if it's a given, then you have this formula, right? So how this formula come from? Okay, so RT, I mean, so this formula and the previous ones are also the same. Okay, and then there's the X, Y, your G is equal to that. Okay, and then now you're going to take Rx. If I take Rx, this is 1, 0, and then G prime. G prime X. Okay, and then I take Ry, 0, 1, Gy. And then I take the cross product. I just use the X and Y instead of U and V. This is I, J, K, 1, 0, Gx, 0, 1, Gy. And then that becomes equal to Gx. To save time, just tell you this. You know, just do the cross, just the vector. Okay, so now you can just I had to erase this part. So then I take the length of that. Take the length of this. It's kind of funny to exercise. I like this one a little bit smaller. It's a cross product here. So that's just equal to I use an F. So this is G. Because I use a G equal to F for X. I use a G equal to G of Fs. I don't want to kind of. This is what we did before. In chapter 13, we use F. And then plus 1. So you can see this is just equal to that, okay? So that's how you prove that. So that's sorry about the long video.